All right. So yeah, even if you're not done, pause, there will be time later. It's very important, I think, that we watch this. So I'm going to go through it, and I don't want you to copy it yet. I will leave it up here for you to copy. I think the important part here is that you listen. So what we're going to go through here is the foundations of the unit circle. And we're going to abstract all the principles we need that we're going to apply in chapter 5 and 6. So this is very important. So we've got the Cartesian plane. All right, here's the y-axis, here's the x-axis. And we've drawn a circle that has the center 0, 0. A point of origin is the center, and it has a radius of 1. Okay, so let's just fill in a few very basic things. What are the coordinates of this point here?
1.
X is 1, y is 0. Good, okay. How about up here?
0, 1.
Good, 0, 1. All right, and I'm just going to go through and do the rest quickly. Minus 1, 0, and 0, minus 1. Okay, so remember when we write the set of coordinates, x comes first, then y. Okay, pretty okay. Now let's consider point P. And it has some x coordinate and some y coordinate. We don't know what they are. And its position is dictated by some angle theta. So I'm going to put point P here to begin with. It could be anywhere along the outside of the circle. All right? And its position is given to us by this angle. All right? So if theta is not, let's say if theta is 70 degrees, point P is going to be here. All right? If theta is 120 degrees, P is going to be over here. If it's 180 degrees, all right, so the position of P is dictated by angle theta. All right, very good. Now, let's see if we can determine what are the coordinates of point P. What are the coordinates of point P? And we're not going to do it for a specific point, we're going to do it for all possible points, all possible positions that P could occupy. So, what I'm going to do is, if I draw a line straight down here, you can see we've got a right angled triangle. And I'm going to take that triangle and I'm just going to pull it out of the unit circle and sketch it here so we can see it nice and big. I've got, this is my angle theta, this is my point P. All right, I'm going to fill in as much information as I can. What's this distance?
1.
1. Kevin's right. How come it's 1? The radius of the circle is 1. Very good. This has a distance of 1. Okay. How about, in terms of how I've described the problem, what is this distance? Yeah, we're not going to label the triangle just yet. What's the distance?
Less than 1.
It's going to be less than 1. Yep, that's correct. It's going to be x. Okay. So it's going to be x. All right. Because if you think, how far have you moved across here? Well, whatever that x coordinate is of point P, that is how far you have moved across. Okay? How about what's going on here? Well, that's how far you've moved up. It's going to be whatever that y value is. Okay, so that's the triangle. There, that's the information we have. They're sort of the unknown sides. And now, let's label it like we would when we're doing right angle trigonometry. We've got the hypotenuse, the adjacent, and the opposite side. Okay? And let's think, all right, we have the trig ratios of SOHCAHTOA, aren't they? And let's, what am I trying to do? What's my question is, what are the coordinates of P? Well, P has an x coordinate x and a y coordinate y. Let's say I'm trying to solve for x. I want to get x by itself. So I've got x. I don't know y. Y is some unknown, so I'm not going to use that. I'm going to use this one. So I've got A and H. A and H. Which ratio uses A and H? Cos. All right. So we have, I'll come over here, cos theta is A on H. In our circumstance, this is, I'm going to go sideways, cos theta is x on top of 1. Okay? X divided by 1 is the same as x, right? So we have x equals cos theta. pause for dramatic effect. This will tell you the x coordinate for any point along the outside of this unit circle. The x coordinate is equal to cos of whatever the angle is. All right. Let's try it for sine. Let's try it for y. If we're trying to get y by itself, okay, we've got O and H. So if we got y by itself, we'll use sine theta is O on H. So sine theta is y on top of 1. Y is sine theta. Okay, so for the unit circle, any point on the outside of the unit circle, any coordinate, the x coordinate is cos of the angle, the y coordinate is sine of the angle. Really good. Okay, we're going to just get the other two properties as well. If we were to do, so we've done sine and we've done cos, how about this other ratio? We've got tan theta. Tan theta is O on top of A, which is y on top of x, which is sine theta on top of cos theta. Okay, so tan theta, the definition of the tan theta ratio is sine theta on top of cos theta. So I'm going to just draw a couple of boxes around the things that we need to know. There's one more identity that we're going to derive here. It's the Pythagorean identity. If we look at this right angled triangle, all right, we would have x squared plus y squared is 1, right? A squared plus b squared is c squared. So that's an application of Pythag. What is x? X is cos squared theta plus sine squared theta is 1. Okay, so just a word on notation. When you have cos of theta squared, that's the correct way to write it. That's the case for any trig ratio. Plus sine theta squared, that's how we express it. Okay, so we've got a couple of identities we've unpacked here. The Pythagorean identity, we've got the definition of tangent, as well as the coordinates for x and y on the unit circle. Okay, so that's how we develop the unit circle. So let's go back then to what we started filling in. If we think, what are the things that we had? We had the first quadrant, we've got here 0 degrees, and we know it's going to be the same in radians, 0 radians, and the coordinate was x is 1, y is 0. All right, if you put in your calculator cos of 0, cos of 0 is 1. All right, remember, x equals cos theta. At this point on the circle, the angle is 0. Cos of 0 is 1. Sine of 0 is 0. Okay, let's move on to the next point. We've got 30 degrees or pi on 6. So there are two angles, and there are two settings in your calculator as well. It doesn't matter which one you use, as long as if you're using degrees, your calculator is set in degrees, and if you're using radians, your calculator is set in radians. So I'm going to say this a number of times throughout the unit. You need to be competent at switching between both, because you will use both. So I'll show you how on your calculator do you switch to radians. You just press Shift, Menu, and you scroll down to where it says Angle, and you can alternate between degrees and radians. Okay? So if you're given an angle in degrees, you need to make sure your calculator is set in degrees before you put it in. If you're given an angle in radians in terms of pi, you need to make sure your calculator is set in radians. Okay, let's all set it to radians, and we're going to go through this one. All right? So I've said we've got the coordinates here and they're blank. We want to know the coordinates when the angle is 30 degrees or pi on 6. Now we've set our calculator to radians. So that means we need to input the angle in radians. to find the x coordinate here. X equals cos of theta. What is our angle for the first one? Pi on 6. What is our angle in radians? Pi on 6. So we put in cos of pi on 6. Alright, that's going to be our x coordinate here. You put that in your calculator, evaluate it. Root 3 on 2. Okay, we want them expressed exactly. How about the y coordinate? The y coordinate is sine of theta. So it's going to be sine of pi on 6. You put that in, half. Okay. Move on to the next one. The next angle is 45 degrees, or in radians, that's pi on 4. Cos of pi on 4, 1 on root 2. Sine of pi on 4, 1 on root 2. They're the same. I've got a couple of things to say about that one. I'm just going to clear that. 45 degrees, okay? If the angle here is 45 degrees, and this is 90, it means this angle is 45 degrees as well. It means we have an isosceles triangle. It means these sides are equal to one another. X is cos of 45, y is sine of 45, and we notice they have the same value. Of course we expect that to be the case. Now, that's the first thing to say. So at multiples of 45 degrees, all right, you expect the x and y values to have the same magnitude. Okay, and the second thing to say is, I wrote 1 on root 2. Another way you will see it expressed, sometimes by your calculator, is root 2 on 2. They mean the same thing, and you can check by converting it to a decimal. You can check that they are the same. I don't care which form you use, they're the same, okay? But we'll learn, I might explain why they're the same during another lesson. All right, so I've shown you how we can generate the angles. I'm showing you how we can generate the coordinates. Now, let's talk about what do we expect to happen as we move further around the circle here, all right? In this section, we've got both x and y coordinates are positive, all right? So we expect all of those coordinates to be positive. Over here, it's not going to be the case. Something's going to be negative. The x coordinates are negative, aren't they? Because they're less than 0, they're to the left. So that's what we expect. We expect the x coordinates to be negative. Down here, we expect both x and y to be negative. X is negative, y is negative. And then in this last quadrant, we call each of these a quadrant. In this last quadrant, we've got x is positive, but y is negative. Okay, so what I want you to do, and it's worth doing, because it helps us to start operating with these kinds of definitions, is fill in the rest of the angles and the rest of the coordinates for your unit circle. We're going to start to notice some patterns before we get into the application. Okay? So you've filled in the angles already, fill in some coordinates, or finish filling the angles in.